So here we're talking about different types of machine learning algorithms, and the machine learning has been divided into different types of algorithms and different types of techniques and strategies. So we're talking about supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, primarily you're going to have a volume of input data. It could be, array of numbers or array of text or vectors of, anything that you want to take the data input, and then basically you're going to have different types of labels for it, and the system learns the function, and it basically maps it. Let's say here a text, and then you're going to have multiple columns. Each text column will have a separate class label, and the function will now be able to predict the output Y from heterogeneous input data. And again, there is an amount of accuracy that we're going to get, and also, how that training process gets converged in the supervised learning is important, because that's when you can get more accurate outcomes. And again, unsupervised learning, and semi-supervised learning, you have a combination of labeled data and unlabeled data. And again, we're talking about unsupervised learning is, again, where there is no labeled data. Now moving on to reinforcement learning. Reinforcement learning landscape is primarily defined by the tuples SAPR and the gamma. So in reinforcement learning, basically you have an agent, and the agent is computing different types of calculations, or learning the environment of how to navigate into it, and how to reach the goal. So basically agent has a goal in the environment. So the primary objective is to achieve the goal. And so the agent, every time goes to the environment, is given a set of states and set of actions. So, and some of the type of environments is where there are observable environments. And again, if you're talking about space, or if you're sending some spacecraft to Mars, and again, it's landing into an environment which is unknown. So that becomes only a partially observable environment, as opposed to be completely observable environment. And again, the agent wants to optimize the reinforcement learning, and this is given by the reward function S into A that yields into R. So basically, S is your states and A is your actions. And the probability defined here is the state transition probability. And we also, as I explained, NASA has sent several spacecrafts to Mars. And so the agent, when landing onto such landscapes, would not know the type of gravity there, or how it can perform the landing, and how they can go to the Mars. And because it's a partially observable environment, you can't completely see the environment. So we can see those type of examples as we go forward, different industries, how they're potentially leverage these type of processes. Again, now coming back to reinforcement learning, the entire reinforcement learning has been laid on the foundations of Markov decision processes. These are the mathematical foundations. It's not like it has a lot of memory, like most of the conventional algorithms keep a lot of track of memory, and then leverage the memory, and then perform the function approximation and different types of optimal value functions for state and action pairs. But coming to reinforcement learning, it's memoryless. It's not like, you're gonna feed lots and lots of data. I mean, initially you will have some sort of, data, like for example, in robotics, like several companies like Google, OpenAI have implemented reinforcement learning algorithm. There will be some offsite learning just so that they get familiar with the type of state and type of action. But again, it's the agent that has to dynamically determine the state and action at the runtime. It's not like you can always have, a defined specific action that the agent can take. And again, so in the way that fundamentally it has been modeled is on the infinite horizon. So especially if you're talking about going to another planet, it's not like you have a defined and a known set of horizon. It can expand as much you go forward, so it's infinite horizon. And again, you can have a finite horizon. For example, if you're operating a car, a driverless car that needs to operate on the roads, then you have a specific finite state space and finite action space. Again, you have a continuous space and you have discrete space. It all depends on the type of environment you're leveraging for the agent to take specific actions and get the rewards. And so the reward function is primarily every time the agent gets it right, is going to receive a reward. And if the agent performs some wrong action, then basically it's going to be deducting and having a penalty for it. And there is a discount factor, which is a cumulative discount factor. And you can take a look at Bellman equations to understand more about how the cumulative discount factor applies in the environment. And the delta S is primarily the initial state distribution. And so again, how we can apply for businesses. So in order to get the business value, the companies that are primarily operating in today's world and the supervised learning need to move towards the reinforcement learning. That's when they can actually leverage most of the deep neural networks instead of leveraging the Q learning, which is only operating on a set of neural networks which cannot produce the type of outcomes and predictable interactions that you're going to have. And again, we are talking about the cars to operate driverless cars. So if you're taking a driverless cars, it requires LIDAR. So again, LIDAR is a light range detection technique that will just throw the pulse of lasers around the objects, and it gets the momentum of the object in the surrounding environments, and that's how it knows how to navigate into the roads and different types of environments. So that operates with, that's why it's very important to have LIDAR sensors, especially if you're leveraging driverless cars and it needs to compute reinforcement learning techniques. And also spacecrafts and UAVs can land on different planets and they can navigate on their own on an infinite horizon, but again, not completely observable environment. And again, this is not limited to a specific industry. It can be implemented for any consumer with recommendation systems for, like, if you're talking about e-commerce or somebody like eBay, a lot of companies have been successful in doing it. We're going to take a look at it. So this is, again, we're talking about OpenAI robotics here on the left-hand side. As you can see, the robotics can do the finger pivoting, sliding, finger gating. How they're able to achieve it? They're all able to achieve it just through reinforcement learning and understanding the environment. And again, it can be also implemented for quantum computing. There is a quantum reinforcement learning, which will be a separate topic. But again, it can be implemented for several fields, and people have been successful with production deployments in doing that. So again, coming to the reinforcement learning is nothing, something that is coming as a new term. It has been around from 1950s, and there has been a major shift towards the machine learning from the 90s, and so a lot of times back in the days in 80s, so people have written a lot of programs with millions of hash-coded rules, and they only can compute, so many types of permutations and combinations, and that's exactly, they create all the rules for them to be able to produce the outcomes. But again, it wasn't very effective because the systems are just knowledge-based systems and not really practical oriented systems to understand the different type of, the risks and the type of, the sudden evolution of dynamic landscapes and several conditions that can arise. So again, there has been a AI cold winter for a while because try to move away from the knowledge-based systems and try to move to something towards more practical. And so again, given the common sense of the machines require more than just powering the system with knowledge-based systems, but something where it can just take a pile of data and learn automatically from the machine and then produce the outcomes without any intervention with label data. So again, that's why there have been several types of algorithms that have been created over the years. And we're talking about Bayesian networks, we're talking about bio-inspired algorithms, we're talking about evolutionary algorithms, genetic algorithms, Markov methods, and support vector machines. So as the machine learning research engineers started to build several algorithms that can produce outcomes, especially that can handle large scale volume data as opposed to be dealing with small data, then there is a need. And as the big data has been, creating a tsunami of data from the recent decade and, a couple of decades. So that's when people actually started moving towards the deep neural networks, because they realized that, just running through the neural network with a specific limited number of networks, it's going to be almost impossible to calculate the type of calculations, especially if you're dealing with supercomputing. And back in the day, like in so if you go before deep neural networks, so before 2000 or 2010, people used to create these nuclear bombs, and then they had to annihilate all the islands, and they just create so many holes. Because why they were able to do it? Because you just cannot simulate a bomb creation. So how they were able to do it? Because as we move towards the deep neural networks in the field of supercomputing, they were able to create all the mathematical combinations of how the explosion actually looks like without having to annihilate all these islands. So that's when the simulation of bombs have started in 2000 onwards, 2010 mostly. And that's what we are seeing. The neural networks have been shot to fame in 2012 with deep learning technique and a number of neural networks. So you can create neural networks as many you want, and there are no limitations in terms of creating the neural networks. So this is an example where the robotics in OpenAI and Google are able to operate and learn on their own, how to pivot, how to slide, how to gate, all of these actions that they can primarily learn on their own with reinforcement learning. So again, several companies have potentially leveraged, the Kindred AI is a robotics company, and they have implemented a lot of robotics with reinforcement learning. And AlphaGo is again a DeepMind initiative where they have created a robot. Primarily, the robot can operate on a AlphaGo board and compete with the actual human being, and can win or lose. So we're going to take a look at and again, OpenAI agent is another. They create a lot of environments for reinforcement learning, and they created a number of environments to operate, and they've been successful in creating several types of environments, and where the agent can navigate without manual interventions. Again, AlphaStar is again a part of one of those examples where there have been successful outcomes from that. So we can say that the third and final shift in the artificial intelligence has been the reinforcement learning, where especially in 2015, the DeepMind's AlphaGo has been successful in the way that it has been constructed is with Monte Carlo tree search algorithms. So the Monte Carlo tree search algorithms can, before the other person can think about a move, how to make a move in the AlphaGo. AlphaGo is similar to chess, but not exactly the same, but it is more complex with more number of combinations. So before the other person can think, it traverses and pivots through so many Monte Carlo search algorithms and finds different types of combinations and permutations of millions of moves. And it knows that what are the all possible combinations the other person is going to make the move. So, and then it can successfully implement the strategy and roll it out before the other person can do it. So in doing so, it actually has been, there was a AlphaGo game, and where it has defeated the European Go champion with 5-0. And a lot of other human professional players have lost to that, because they can't possibly think so faster because of the time that is there to make a move in the Go board. And the other thing is that even if they can think faster, they cannot think of the possible combinations of how the other person is going to come and make the moves. But that's what makes it more complicated. And that is where, the reinforcement learning, especially the deep reinforcement learning wins. It can make predictions with all of those combinations. So if you take a look at the machine learning pipeline of AlphaGo 0, you can see, how it creates this rollout policy, and it creates a policy network and a rollout policy network and a value network. And it performs itself so many combinations, and it knows if this is what's going to happen, this is the move, if that's the move, so on and so forth. So it does all the training on the deep neural networks, and so it knows how to compute and perform that. So again, as we have moved into deep neural networks, the large data sets have hit the roof on the reinforcement learning, trained on the x86 architectures, ARM processors, GPUs, and FPGA accelerators. And so now, that's when the reinforcement learning comes to rescue. So earlier, AlphaGo has, created this neural network, and it primarily created, something like a couple of neural networks, one that competes with the other, and then it can play itself to predict all the types of moves that are possible, so that it can have a look into the future. So it knows that these are the type of combinations that it can expect. And, basically that's how it actually creates the demand generation of multiple moves, and it can actually, and again, it's implemented with policy gradients. And we're going to take a look at what are policy gradients, and it's like a strategy that it defines how to operate. And so that's a policy for the reinforcement learning. And again, it gets trained on the neural networks, and it can take those policy networks and the combinations as input features from just the black and white show that it has on the board. It knows that these are the input features, and it takes it and then it predicts all the combinations through Monte Carlo search algorithms. So now, how do we know that reinforcement learning is on the rise? So again, the reason why we know that the reinforcement learning is on the rise is because MIT Technology has performed recent research, and they've actually downloaded 16,625 research papers. And so basically the way that they try to do it is they actually have looked for natural language processing by taking some of the keywords like theory, rule, logic, program, and several other combinations, including the reinforcement learning. And and it was able to see the trends, and the trends actually have showed that it was able to find that reinforcement learning has been on the top from a decade. And that's because every other company has started moving away from the supervised and semi-supervised and unsupervised learning and started moving towards the reinforcement learning. And that's when there are more heavy implementations of reinforcement learning algorithms that are, come into the picture. And so again, this is a project where it has been implemented by MIT. And in this project, primarily what they have done is this project, they're completely crowdsourced, so that they just didn't want to build it by themselves. They want to invite, it's type of a hackathon where people are invited. A number of data scientists were asked to participate, where they can take a competition and create a deep reinforcement learning algorithm where the cars are operating on a multi-lane freeway. And so there is a model-free off-policy reinforcement learning that has been done. As I mentioned again, the reinforcement learning requires sometimes some type of off-policy reinforcement learning training, so that it at least understand the basics of the environment. Then it starts figuring out itself how to navigate and So basically, the way that these many people have implemented, they have implemented training of 96 years of reinforcement learning simulation, which is not humanly possible for a person a single data scientist to come with. So it's an entirely teamwork of all of these, data scientists that have created such type of 96.6 years of reinforcement learning simulations. And how many parameters did they look at? It's like 572 million. DQN hyperparameters have been fine-tuned to train the agent successfully. And primarily, this was trained on the Mojave environment. And so it has also been trained for DeepMind has trained it in different types of environments. For example, like arcade gaming environment, Atari gaming environments, and the front end has been completely implemented in JavaScript. A lot of people ask me, why do we, talk about React.js, and why do we talk about, JavaScript or any front end? Because most of the times when you're building such environments, it's much easier to build a front end in JavaScript. For example, this particular project has been implemented entirely in JavaScript, leveraging full stack development with React.js, Vue.js, a number of JavaScript libraries and packages. And that's when you can visualize all of these outputs and outcomes from that. Of course, you can leverage PyTorch and Python, where we're going to leverage libraries like Matplotlib, for example, is where you can compute and display. Or if you're working on TensorFlow, you can leverage the TensorFlow board that has different types of visualizations. But again, it gets really complicated when you have to build such complex reinforcement learning environments. So it's best that you're going to have a JavaScript as a front end for you to build such environments. Again, they also asked me why, we talk about IoT and IIoT. Again, this is primarily, you can connect it to any IoT environments, and you can also get, the data captured from sensors, and you can also transmit that and, build through JavaScript, and you can compute that. So the way that this has been implemented is with a Q function. Again, deep reinforcement learning is nothing completely different from the primary Q learning. We're going to still take the Q function mathematically, and we're going to implement the deep Q learning with that. But again, the way that it works is slightly different because it's trained on a number of deep neural networks as opposed to be working on specific neural networks which are limited in machine learning. So here we're going to take a Bellman equation, and we're going to get the updated return, and we're going to predict the return, and then we're going to compute how it's going to operate for each episodic iteration in the policy. So again, so what we're going to talk about the policy. So the policy gradients are, you can implement for a number of purposes. Again, you can do it for distributed parallelization of your algorithms. And so primarily you're going to define your policy, and you're going to have all the algorithms with either synchronous, or you can define asynchronous reinforcement learning algorithms. And you also have different types of policy gradient optimization algorithms. For example, we're talking about TRPO, which is trust region policy optimization. And we also have a number of policy, optimization reinforcement learning algorithms you can have. And, you're going to get the expected return from it, and you're going to have finite horizon undiscounted return. And you're going to have policy gradient, which is the gradient of the policy performance. And you're going to compute the stochastic parameterized policy. It's stochastic because it's so dynamic environment, just like, the stocks, they just rise up and down throughout the day. You don't know what is the pattern that is. You can't have a specific pattern to be adopted. That's how the agent also actually moves in the environment. You don't have a specific, it's going to be completely dynamic. And based on the dynamic policy, you can optimize and create a gradient ascent for it. And basically, you can have a mathematical expression of the policy gradient, and you can compute it, and you can derive it, and you can calculate the sample estimate. And then again, in this case, we're going to operate on a finite horizon as opposed to be operating on a infinite horizon. So there are several equations that are very important for us to know before we actually start implementing the policy gradient algorithms. And primarily, there are 5 equations that can be implemented with the policy gradient. And so we're going to talk about the trajectory probability. So you're going to take the, let's say we're going to define the trajectory as T, and then we're going to take all the states in action. So let's represent the states as ST and the actions as AC. And we're going to start computing, and that's your trajectory path for the probability. I mean, whether a car operating through LiDAR sensors or a spacecraft operating on a Mars, it doesn't matter. But you can take any example. But basically, you need to define a course of the trajectory part. And then you're going to actually define the log derivative for it. And you can define the log derivative rule based on the calculus. And again, you can apply the chain rule, and you're going to get the following equation here. You can derive it. And then you can also have a log probability of the trajectory. Once we define the trajectory probability, we're going to start defining the log probability for it. And again, the log probability can be computed as follows here. And then we're going to take the states and actions, and and then we're going to define the gradients of the environment functions, and then we're going to define the gradients of the probability. Once we do that, then we're going to have to define the gradient log probability of a trajectory based on this equation. So once you build all of your mathematical equations and you get that completely ready, then you can actually start coding that in PyTorch or Python or TensorFlow, and then you can start applying these equations, and you can train the agent on the episodic iterations, and then you can actually optimize with a combination of different hyperparameters till you get the best predictable outcome, and where the agent has actually maximized the number of reward functions and able to achieve and reach the goal. And so again, we're going to take a look at different industries that have been successful in adopting the reinforcement learning. And if you're going to take about healthcare, Intel has been the pioneer, and they have been, leveraging the reinforcement learning in the industry, and they have applied it for sepsis treatments, and which is primarily a leading cause of the mortality in ICU. And they have been successful, and they have conducted a number of clinical trials, and their clinical trials have shown some promising outcomes in terms of how they're able to benefit from the sepsis treatments from the reinforcement learning. But they haven't released it to the public yet because they're still conducting more clinical trials to fine-tune the algorithms and be able to introduce in the market. And again, it's not limited to healthcare. It also has been introduced to several industries like manufacturing, industrial IoT, robotics, text mining. And we also have already taken a look at robotics, where Google and OpenAI have implemented the robotics. And again, manufacturing, we have also seen Kindred AI, which is primarily, it operates on, you have several areas in the industry where they need to move containers from one place to another. So the robotics will simply learn how to move these, and then they can start picking up and moving the bridges and boxes and containers from place to another place. So that's how industrial IoT and manufacturing industries have been taking the potential of it. And again, the grasping of the object by the robotic arm is again through the reinforcement learning. It knows what object and how to pick it up and how to move it to another environment. And again, the failure of picking up such objects, is something where there is there's a gap. And it has been implemented with QOpt and DQ learning, on policy and off policy reinforcement learning algorithms. And so basically, OpenAI has implemented this for Dactyl. And the Dactyl we have seen already, where it teaches the humans for dexterity, for finger pivoting, sliding and gating. And there's also another company called like Salesforce that has implemented for summarization of contextual text generation models to produce highly readable summaries of long text. So here is the taxonomy. When you want to master the reinforcement learning algorithms, it's very important that you take a look at all of the different types of reinforcement learning algorithms. Again, a lot of environments are modeled after a specific environment. Or we're talking about like Cartpole environment, we're talking about like a continuous mountain environment, or the roads where the cars operate. These are all model-based reinforcement learning environments. And again, you can have a model-free reinforcement learning environments. And so primarily, if you're going for policy optimization, we just spoke about policy gradient, A2C, A3C, actor to critic, and actor actor and critic networks. So that's a type of policy optimization. And we also talked about trust region policy optimization. And again, the policy optimization has something like DDPG, deep deterministic policy gradients. And we also have TD3, which is a temporal difference learning. Again, there is a temporal difference learning which has been there from 1950s and 60s. And then again, recently the TD3 has been leveraged in implementing policy optimization. So that's why this is a redefined method, and how it can be implemented. You can take a look at that. We already are talking about the DQN, and there's already a C51, and then there's a quantile regression DQN. This is a completely different type of DQN, deep Q learning. And again, we're going to talk about the synchronous and asynchronous algorithms we talked about. And so these are the type of I2A, MBMF, MBV are the synchronous and asynchronous type of reinforcement learning algorithms. Again, you're going to get complete implementation of all of these algorithms and techniques and different environments in my upcoming book. You can take a look at it and then see how you can actually potentially leverage these algorithms. Again, my book is going to be in PyTorch, but again, you can implement in Python or TensorFlow as you like. And you can find more information in my upcoming book with actual implementation samples. Okay, so what we want understanding is, why there is a difference between Q learning and deep Q learning. So as I mentioned, Q learning has been there, run for multiple decades, and deep Q learning is something where we're leveraging the deep Q neural networks, but fundamentally, the foundations remain the same. It's not going to be extremely different, but it's the way that you're implementing your Q learning function is going to be slightly different in terms of, how you're going to train the deep neural networks on the Q learning. So that's what makes deep Q learning more efficient and highly accelerated, especially when you're calculating all your accumulated rewards. It's going to be exponentially high in terms of, especially with talking about large data sets, and we're talking about large scale big data, then you're going to have to need a lot of memory, millions of states and actions would be needing. And that's when you need deep Q learning. You can't just, have it. And again, you need to have it's called memory buffer replay. So it shall be able to understand all of the states it has performed recently and go back and look at it and take a specific action. Especially that's possible only with the deep Q learning. So the buffer replay is something where it can, for example, if you're having alpha star, or you're going to have, the tactile, or you're going to have different types of these games, OpenAI and DeepMind has created arcade gaming. So there are millions and millions of states. So it's only possible with deep Q learning we can achieve such kind of outcomes, and that's when you need the deep Q learning. Again, Bellman equations you can refer and you can understand. And I'm going to be giving a very, very deep introduction. From starting from somebody who just would like to get started with deep learning and deep Q learning, and also providing all the Bellman equations, and I'm also providing all sorts of statistics and mathematical equations, so that it becomes really easy when you actually go to the program. Because what we are thinking, but again, it's some of the most brilliant and brightest minds have created these algorithms, as I mentioned, from 1950s. And it's not like we can do this like a crash course over a weekend, but that's why when you get the book, you can read it and you can actually go through it and step by step understand how to implement it and what are all the prerequisites the person needs to have. I created a list so that you can get completely equipped with all of the prerequisites before you can actually go and implement them. So again, our main topic, coming back to FPGA. So this is how it has been implemented on FPGA algorithm. So if you see on the left-hand side, this is the Xilinx FPGA chip, which is a PYNQ-Z1. So the Zinc SoC basically has a Python application, and DMA drivers. And you can also implement in TensorFlow or PyTorch. It doesn't matter, but it just, you can embed your code onto the FPGA and you can run through it and you can get the outcomes on the deep Q learning. So you can implement, for example, like Cartpole environment and you can see the output. So why the PYNQ-Z1 FPGA board platform is more efficient as opposed to be, running it on a regular, GPU or something. So the reason, again, it's more efficient is that, it needs, as I mentioned, the experienced player to kind of understand, all of the different type of states that it has been operating for a while and how it can go back in time and, take a look at all of the states in different memories. And then basically it will take the sample from the distributed parallelized memories, and it can, so it can actually eliminate the BIOS while it actually processes it, because it takes the sample so that it's evenly distributed and, it's going to get much better, especially operating in stochastic environments, which are more dynamic. And so again, basically the way that deep Q learning, it has a source network, and which is a prediction neural network, Q network, and then it's going to create another target Q network. As I mentioned, even AlphaGo has done the same thing, or AlphaGo has done the same thing, primarily operating on two types of neural networks. One is a predictor Q network, and then there is a target Q network. So in the predictor Q network, you have all of your algorithms, all of your input features where it gets it, and then it starts producing a target Q network, and then it starts training them. And again, if you take a look at several other examples like Atari 2600 game, it was trained with deep Q learning by DeepMind with stochastic gradient descent and backprop, and then again forward prop. And it has updated the states and it has updated the weights in the arcade learning environment. And so again, we are implementing it with the backprop here, and upon the large scale buffers, we can do the episodic optimization. And a real world project with ARM Cortex processor, starting integrating with FPGA devices with Xilinx PYNQ. And on this, basically, we can take an OpenAI gene, for example, as I was talking about the Cartpole environment. You can take that, and if you can actually run it on any CPU, and then you can benchmark it, and then again, run the same Cartpole algorithm with deep Q learning algorithm, run it on the PYNQ-Z1, and you can actually see 126 times improvement with a conventional algorithm. Again, when you can also do another project on the same PYNQ-Z1 Xilinx, where you're actually leveraging the extreme learning machine method, and you can do an online sequential ELM, and you can just completely avoid the backprop and then just go on the ELM and try to see how much you can gain the training optimization, and then compare it again with deep Q learning, and then that's when you see actually 126 times improvement with deep Q learning on this particular FPGA board. So again, in order to implement this on the ARM, as many of you might be aware that ARM has been recently acquired by NVIDIA. So most of the, they're still in the process of, integrating all of the libraries between ARM and NVIDIA. But again, for this, you need to very strictly stick to the ARM ecosystem for this. And primarily you can implement it in several combinations of TensorFlow or MXNet and Apache MXNet. And then you also you can implement with PyTorch, you can implement with Cafe tool, and it also has Onyx Android APIs for you to implement it. And ARM has a specific ARM compute library for FPGA. You can take a look at it and see how you can optimize and implement for that. And again, ARM also operates on GPUs as well and CPUs. And for CPU, you have Cortex and Dynamic IQ NeoVerse. And for NPUs, you have Ethos. And you can also implement with several digital signal processors or FPGAs and accelerators, where you can get a lot of integration with ARM hardware. So I'll take a brief moment here and pause and open up the discussion for any questions from your side, so that we can go through.
Thank you. Thank you for the presentation. So let me make sure. Okay. I'm sharing my slides here. So let me make that a full screen. So when you do the presentation, it's the two books you introduce to, as some, reading materials for your work. I want to, double check. That's that's the two books I found at Amazon. So if that's some additional learning materials we can share.
Yes.
Okay, cool, very cool. Okay, so I think this is a very good topic. So comparing with machine learning, deep learning with the ARM system, it's kind of really critical, especially software and hardware together. So my question is, can you share some idea, what you can see in maybe next 2 or 3 years, what is the direction for this, research?
Yeah, certainly. As we have seen, the GPT, which has been created by OpenAI, there's a GPT-2 and GPT-3. So these are the future of singularity, where a lot of people are talking about reaching towards singularity. So right now, the GPT-2 and GPT-3 can actually implement a lot of natural language processing abilities, and they can take the entire data, and then they can actually predict. For example, it can take a few of the chapters of the book, and it can predict the next chapter, how it's going to look like. And it also can actually create press releases, and it can actually also create several types of algorithms with the text, and it can predict the data from that. So if you're talking about singularity, again, that has to be something like a GPT-1000 or something, because the current, maybe the processors are not scalable enough, or the data that it processes right now has hit a computational limit on the hardware and software right now, where people are trying to accelerate every quarter. The amount of processing power required by the deep neural networks is actually very high, but it is not able to achieve it because of that. And you can find more about that in the Future of Data Science book as well, the parallel computing. That's where actually it's going to be, quite complicated to achieve the singularity right now. But that's where we all believe that, the machines can actually perform several such tasks which are not possible for a human or a machine to create. Again, this is not about machines replacing humans or anything. This is humans always have the ability to program and be able to come with certain future outcomes, and that's where we can have more. It's like actually going to increase more jobs with AI, because it's just the way of doing things is going to be different. Traditional information technology, people are operating several companies, several information processing companies are dealing with the data in a specific way right now. But again, it's about reskilling all of the people into a different way of doing the things. Again, the reskilling is where taking the path to the data science and AI, where they're going to be reskilled and be able to have all of the programming frameworks and different types of combinations of streaming platforms, like maybe Apache Spark, Apache Kafka, Apache Flink. All of those platforms integrating with IoT and IIoT is specifically where they can leverage and implement a lot of these algorithms intuitively. And that's when we can actually have such type of outcomes that can happen in the future.
Okay, thank you for your comments. We have one question from our attendees, from Glenn G. FPGA, how big the data science it can process so far?
So FPGA, again, has Xilinx, and there's also AMD. As you know, AMD is actually acquiring Xilinx right now. Xilinx is the biggest company, which is San Francisco-based company, that has been producing all the FPGA accelerators in the in the today's world. And the FPGAs actually have been implemented for nuclear bomb simulation, and FPGA have also been implemented for plasma turbulence, and so such kind of for example, like the world is right now trying to process with different type of so for example, conventionally we want to produce energy. So we want to produce energy, and the energy we are producing is not sufficient enough in the market to do different types of things. And so what the world is doing right now is basically able to try to produce energy from the nuclear energy, because the nuclear energy has no limit. It's just like the process that sun processes. Inside the sun, you have the way of nuclear fusion where it generates the energy. And what if you were to leverage such energy process from the nuclear fusion and able to produce the nuclear energy? So that's when a lot of industries have been trying to produce that nuclear energy with the supercomputing distributed applications. And that's where FPGAs have been heavily leveraged right now. So, you can take a look at a lot of projects from, Livermore Lawrence laboratories from the supercomputing. And you can also take a look at, few other supercomputing labs where they have been leveraging the FPGA accelerator. The amount of data they are actually operating to compute the nuclear plasma simulations and plasma turbulence is just immense, and you can't even measure it with any other type of data, because it produces so many types of simulations that gives different atomic combinations that can create the nuclear energy process, nuclear fusion especially. So when they produce it, the heat gets so high, it actually recreates the same type of heat you have at the center of the sun. And so for that, they create the tomahawks, which actually they place that can actually resist that type of heat that can be generated on the nuclear plants where they operate this. And all of this is completely processed. All of this data is through FPGAs. And actually, I'm going to provide a chapter on it in my upcoming book. So you can take a look at my first book. You will have more information on that.
Okay, thank you for your response to the question. So I think we have another two questions. The first one, will it be faster than the GPU?
Well, it types of, there are FPGAs, there are ASICs, there is another type of chips called ASIC chips, ASIC, and there is again GPUs. So it all depends on the, what exactly we're looking for. Each type of accelerator is expected to, perform such calculation. Again, the FPGAs as of today are very expensive, because this is not something where people can start implementing it at global scale yet. And that's why are leveraged by, mostly the national, for, defense and national security applications, where they're implementing for, also the transportation of nuclear weapons from one place to another. And they're building this special transporters that can, the truck you might be seeing on the road carrying, carrying tons and tons of nuclear weapons in it. So it all depends on the type of application that people are leveraging, where you can actually go and scale it. The speed is great, but again, is it practically possible to implement for all the industrial grade applications and all the enterprise applications out there in different industries? So that's the question we have. So unless the FPGA price is going to decrease, just like the silicon chips are going like a cent per chip, that's when the IoT and IoT sensors are increasing and in production, and people are able to consume. Even for the aerospace industry, a lot of people are putting all these sensors on the engines, the turbine engines, where they can actually get the atmospheric temperature and different parameters so they can deroute the plane so that they know before a storm that's going to occur. And we actually implemented this for a aerospace client with all of these sensors. And again, those are the type of sensors are regular sensors. But again, if you're going for FPGA, these are still, as of today, very expensive. Unless we see some significant giant leap in the technology that can reduce the price of all of these FPGAs, we're going to still stick with GPUs for industrial grade applications and processing. It's not, as of today, it's very difficult to leverage FPGA chips at a larger scale.
Thank you for your comments. So another question from the attendee. From the processing speed perspective, how do we evaluate the speed and efficacy about FPGA-based and DSP-based deep learning system?
Yeah, so there is actually, when you want to measure the performance of your neural network running on FPGA, or you're running on DSP, so primarily there are several optimizers that are available for our deep neural networks. Like we have something, for example, like Atom optimizer, and the different types of optimizers are Adagard optimizer. So what you do is the same algorithm that you're going to train for, whether it's for reinforcement learning or natural language processing, anything you want to train, you want to run through all of the optimizers and get different outcomes, and then see which optimizer actually can optimize the training to the maximum. That way you're being more effective on the FPGA. Again, you can leverage the extreme learning, machine learning method, but leveraging the FPGA specific algorithm, unless you run through different optimizers, you would not be able to benchmark and say, again, there is a benchmark available if you want to take a look at FPGA benchmarking. I think I shared it in the recent times, probably a few years ago. It gives you a complete breakdown of all of the benchmarks on the FPGA, Xilinx, and all world FPGA manufacturers and their benchmarking for each type of algorithm. So that way we know, but feel free to send me an email or anything. I can actually share you the entire article where you can see the benchmarking of all of these FPGA training algorithms, and which is more effective.
Yeah, that's good. Thank you for your presentation. Thank you again to be our speakers, and we will follow back with you. Other questions from the attendee. So let's see. Thank you for Dr. Ganapathi. So we will go to our next speaker. Thank you all.
Thank you very much to Jason for providing this wonderful opportunity to share these algorithms and upcoming books, and appreciate Jason and the entire audience for going through this. And feel free to send any questions or anything you have. You can just email and get your answers in addition to what we have discussed.